Hello everyone, I'm Peng from the School of Computer Science and Engineering of Hunan University of Science and Technology. Next, I will explain the paper for you. Mobile application recommendation based on feature importance and bilinear feature interaction. My explanation will be divided into 4 parts: background and motivation, research method, experiments and result analysis, summary and future work. With the rapid development of 5G, industry, internet, and mobile network, the number of mobile applications is growing explosively. In the face of such a large number of information-rich mobile applications, it is difficult for users to find suitable mobile applications. By using historic interactive information, such as users' evaluation or comments, we can well estimate the possibility of users choosing different mobile applications. In the previous methods, from traditional collaborative filtering to matrix factorization to extended models based on matrix factorization and fine-grained models based on matrix factorization. Although the above methods have achieved remarkable results in the recommendation system, they mainly focus on how to better interact between features. The importance or weight of the feature itself is ignored. In fact, users have different preferences for different functions. In mobile applications, for example, compared with the price and the scale of mobile applications, most users are more concerned about the score of mobile applications. Therefore, this paper proposes a mobile application recommendation method based on feature importance and bilinear feature interaction. It exposes a Senate mechanism to dynamically learn the importance of features and uses a bilinear function to effectively learn the features' interactions. The structure of the model is shown in the figure. Our method consists of embedding layer, Senate layer, bilinear interaction layer, connectivity layer, neural network, and prediction layer. Among them, the embedding layer firstly embeds the space representation of the original input features into the dense vector. Secondly, the Senate layer transforms the embedding layer into the Senate-like embedded features to improve the distinguishability of the features. Secondly, the bilinear interaction layer models the original embedding and the Senate-like embedding by the second-order feature interaction. Firstly, the connectivity layer integrates the output connection of the bilinear interaction layer into the dense vector. Finally, the cross-combined features are infused into the neural network, and the prediction score is achieved in prediction layer. Next, I will focus on the Senate layer and the bilinear interaction layer. We introduced the Senate mechanism to make the model pay more attention to the importance of features. For specific mobile application recommendation tasks, we can dynamically increase the weight of important features and reduce the weight of features with insufficient information through the Sennett mechanism. As the figure is illustrated, the Sennett consists of three steps. Firstly, the global feature is obtained by the squeeze operation on the embedding feature obtained in the embedding layer. This step is to compress the original embedding into the statistic vector by using the average pooling operation. And then, the excitation operation is performed on it to learn the relationship between each embedding and obtain the weight of different domain embedding. This step is to learn the embedding weight of each domain based on the statistic vector and use two fully connected layers to learn the weight. The first fully connected layer is the dimensional reduction layer of weight parameter matrix, which uses a nonlinear function. The second fully connected layer restores the original dimension by increasing the dimension with the weight parameter matrix. Finally, the final embedding result is obtained by multiplying the original embedding. This step is to reweight, that is, each field of the embedding layer is multiplied by a corresponding weight. The whole operation can be seen as learning the weight coefficient of each domain embedding, which makes the model more descriptive to each domain embedded features. In short, the Sennett uses two fully connected layers to dynamically learn the importance of features. The interaction layer is used to calculate the second-order feature interaction. The classic methods of feature interaction are inner product and Hartman product. The inner product is widely used in shadow models such as FM and FFM, while Hartman product is commonly used in deep models such as NFM. Because the inner product and Hartman product of the interaction layer are too simple to model the feature interaction of sparse data sets effectively. We use a more fine-grained method, combining inner product and Hartman product to learn feature interaction with additional parameters. The interaction vector can be calculated in the following three ways. In field O type, all vectors share the weight matrix. In field H type, parameter matrix corresponds to the weight matrix of the ith field. In the field interaction type, parameter matrix corresponds to the weight matrix between the ith domain and the jth domain. Then, we use the connectivity layer to connect the interaction vectors and infuse the connected vectors into the next layer, a standard neural network layer. In order to further improve the performance, we combine the classic deep neural network component with a shadow model to form a deep model, which can specifically capture high-order features. Finally, a dense real-valued feature vector is generated and input into sigmoid function for mobile application prediction. The experiment uses the open dataset Apostol of Cargo as an experimental dataset. In this dataset, a total of 11 features are selected, including 2 sparsity features and 9 continuity features. Since there is no label in the original dataset, we manually set the label value of mobile applications with a score greater than 3, and the number of people more than 800 at 1, otherwise at 0. The proportion of positive samples is about 0.424, so that the experimental results will not be affected too much due to the uneven distribution of samples. The distribution details of the top 20 categories with the largest number are shown in the table. We select the training set ratio from 0.2 to 0.9 to compare the model performance. When the training set is set to 0.8, the AUC of our model is 19.2%, 20.99%, and 10.22%, 0.27%, and 108% higher than that of MAR, AFM, FAN, NFM, and DeepFM, respectively. In general, our method has the best performance in all models, which shows that, considering the weight of original features and using bilinear interactive learning feature interaction, can effectively improve the accuracy of the recommendation model. We analyze the influence of neural network layers on the model. According to the experimental results in the figure above, it can be observed that when the number of neural networks increases from 1 to 3, AUC has been improved to a certain extent. When the number of layers increases to 4, AUC decreases sharply. From the influence of different neural network layers on log loss, we can find that the same trend, that is, when the layer number is 3, log loss reaches the lowest point. Therefore, we can find that increasing the number of layers will improve the performance to a certain extent. However, if the number of layers continues to increase, the performance will decline. This is because too complex model can easily lead to overfitting. For mobile application recommendation, a good choice is to set the layer size as 3. In this paper, a mobile application recommendation method based on feature importance and bilinear feature interaction is proposed to dynamically learn the feature importance and fine-game the feature interaction of mobile applications. In this method, on the one hand, a more complex bilinear interaction layer is introduced to learn feature interaction, rather than simply using inner product or Hunan product to calculate the feature interaction. On the other hand, for mobile application recommendation tasks, it uses the Senate module to dynamically learn the importance of features, which will enhance the weight of important features and reduce the weight of unimportant features. By combining Senate mechanism with bilinear feature interaction, our model can further improve the accuracy of mobile application recommendation. Through the verification on the open dataset of Kaggle, our model performs best in the most cases. In the future work, we will explore more fine-grained feature interaction and discriminate their importance with different dimensions for further improving the accuracy of mobile application recommendation. Thank you for listening.